An energy diagram is a device that chemists use as a means for visualizing the progress of a reaction. So here's what the energy diagram looks like for the SN2 mechanism. On the y-axis is free energy or potential energy, and the x-axis is what we call reaction coordinate. That's a fancy name. What I like to use instead of reaction coordinate is either progress of reaction, or actually time is another expression that would be appropriate there. So this is an SN2 reaction of Cn minus reacting with methyl bromide to give acetonitrile. And what you should note about this energy diagram is that delta G is negative. Okay, so what that means is that the energy of the products is lower than the energy of the starting materials, or rather that this is a spontaneous reaction. However, even though the reaction is spontaneous, you still have to go over an energy barrier in order to get from the starting materials to the products, and that energy barrier EA is called the activation energy. Okay, so this is an important point to know. Even when a reaction is spontaneous, it still has an activation energy, and sometimes you have to pump energy into a system in the way of heat, even if it is fundamentally an exothermic or spontaneous reaction. Then this little weird thing that you see in the middle is called a transition state. So transition state for a one-step reaction is the midpoint of the reaction. It represents the energy maximum. And if you look at what the transition state for this reaction looks like, you've got a partial bond between the carbon and the bromine. The leaving group has not yet left. You have a partial bond between the methyl group and the CN. The nucleophile hasn't completely approached. Because you have two partial bonds instead of one full bond, the energy is higher. It's not as favorable a situation. And secondly, because there's 5 things in the vicinity of the carbon in this transition state, it's not 5 bona fide bonds, but there's 5 things nearby, that carbon is particularly crowded. So the steric hindrance of this transition state also increases its energy. Transition states are not species that you can isolate, and they're not even species that you can observe spectroscopically. They have a very short lifetime on the order of 10 to the negative 12th seconds. That's really and truly is the midpoint of the reaction. And this double dagger symbol above and to the right of the transition state is the symbol that chemists use in these energy diagrams to indicate where a transition state is. And in a picture of molecules, you'll put that next to the picture to show that that is a transition state and not an intermediate or a reactant or product. Okay, what about the SN1 mechanism? This one's a little more complicated because, as you remember, it's a 2-step mechanism. Okay, you've got a starting material that's got its leaving group, and then the nucleophile comes in and takes the place of the leaving group, and as an intermediate, you have a carbocation. So this is also an example of a reaction that has a negative delta G. The product is more stable than the starting material is, but as you can see, there's still a large activation energy, and relatively speaking, there's probably even a bigger activation energy for the SN1 reaction than there was for the SN2 reaction. So when we say that the carbocation is an intermediate, that is a local energy minimum. So there is a transition state between the reactant and the intermediate, and another transition state between the intermediate and the products that are both higher in energy than the intermediate is. But what you need to know is the carbocation intermediate's energy is much higher than that of the reactants or the products. Intermediates have lifetimes longer than transition state. They are sometimes on the order of seconds as opposed to 10 to the minus 12 seconds. But intermediates, by their definition, are still not stable enough species for you to be able to put them into a bottle and isolate them. They're going to go on and finish the reaction and release that energy and become products. Okay, so each transition state, here we don't have pictures of them like we did on the last slide, but they have a partial bond. So the first transition state has the leaving group not having completely left yet, so there's a partial bond to the leaving group. It's high in energy because you still have the steric hindrance of 4 things around carbon, but you don't have 4 strong bonds. One of those bonds is weakened. The carbocation, even though it has an empty orbital and a positive charge and is electron deficient, that is a little bit lower in energy because you can take the 3 remaining groups and spread them farther apart and reduce the Vesper-based steric hindrance around that central carbon. Then the second transition state between the carbocation and the product is where the nucleophile's lone pair has come in and come within the sphere of influence of the carbocation so that there's a partial bond, but it still hasn't come in hard enough to have a bona fide bond there and the energetic gain that you get out of forming that bona fide bond. So then finally you see that there are 2 activation energies on this diagram. You've got a big one leading from the starting materials to the first transition state, and then you've got a smaller one leading from the carbocation to the second transition state. In order for this reaction to take place, you have to get over the higher mountain peak, the higher pass, so to speak. So the overall activation energy for the reaction is the energy leading up to the highest energy transition state. Okay, in our next lesson now, we will start to look at more of the details of substitution reactions, and we will begin by looking at leaving groups.